We are starting a new topic today, which is kinetic theory of gases. Kinetic theory of gases. Okay. Kinetic theory, there are some assumptions about the motion of the molecules, and this theory says that if you confine some gas molecules in a container, they can move randomly in all possible direction, and during the random motion they will collide each other, and they also collides with the walls of the container. Okay, all the collisions are perfectly elastic in nature, and during the collision momentum is conserved and energy is conserved. These are the basic assumptions of kinetic theory of gases. You know about these assumptions. Now we are considering the fact that they are colliding each other and they are colliding with the walls. So during the collision, they will exert pressure on the walls of the container. Now we are interested in the expression for pressure, which is exerted by the gas molecules on the walls of the container. Okay, so we are moving to derive the expression for pressure. Pressure of an ideal gas. Okay, when you put some ideal gas inside a container, they will move randomly and they will exert pressure. What is the expression for the pressure? Okay, for that I am considering a cubical session. Okay, suppose this is a container. Randomly I am marking the axis, let it be x and let it be y, and this is z axis. They can move inside the container in all possible directions. Let the molecules having arbitrary velocity, say this is velocity v, which is possessed by the gas molecule. Okay, now this velocity have components vx and a component along this direction which is vz, and a component along this direction which is vy. Okay, in all possible direction velocity have a component. I am considering one particular molecule here which is moving along x direction, so its velocity will be vx, right? So vx, when it comes to collide with the wall, after collision it will move back, so its velocity become minus vx. Okay, so I am considering such a molecule. Consider a collection of n molecules in the container. Suppose the length, this length is L, okay, of length L. Their motions are random, so it's very difficult to deal with all such motions. So I'm just taking one molecule, considering one molecule of mass small m. Consider a single molecule with mass small m, okay, which is moving with the velocity v. Velocity v. Okay, what is the velocity? This velocity v is vector which is having a component vx along x-axis, vy along y-axis, and vz along z-axis. This is the velocity expression. And if you square it, v dot v, that is v square, which is equal to v dot v. If you take that, you get vx square plus vy square plus vz square. Okay, we know that the molecule, all the molecules are in random motion, which means that the probability that a given molecule will move along x direction will be equal to the probability that molecule will move along y axis and the same probability that it will move along z axis, which means due to random motion, we can say that the component of velocity Vx, Vy and Vz, they are equal. Okay. All the velocity components are same because they are moving randomly. Each can move in any direction at a given time. So I could write this V square, which is equal to, these are equal, right? So I could write this equal to 3 Vx square, which is equal to 3 Vy square, which is also equal to 3 Vz square. Okay, so keep in mind this fact. Okay, they are in random motion. They comes to collide with the wall. What happened when they collide? Suppose I am taking a wall here. A molecule is coming along x-axis. Say it's having some momentum Vx. When it collides with the wall, its direction will change along this direction. Okay. Suppose it is moving only along x-axis. Then its momentum will be mvx with a negative sign, which means the molecule is moving back. Okay, which means that the momentum of the molecule changed during the collision. Okay, so change in momentum of gas molecule during the collision with the wall. During the collision with the wall. Okay, change in momentum is delta P, right? Which is final momentum minus initial momentum. Change in momentum is by convention always measured as final momentum minus initial momentum. What is final momentum? This is final momentum minus mvx, right? So minus mvx minus initial momentum is mvx. So the change in momentum delta P could be is equal to minus 2 mvx. Okay, so what is the change in momentum of the wall? Change in momentum of wall by Newton's third law, we could say that when the gas molecule hit and impart some momentum on the wall also provides some impact on the ball. So they are mutually balanced. Ball provides some impact on the wall and vice versa. So if ball having or gas molecule having a change in momentum minus 2 mvx, then the change in momentum of the wall should be plus 2 mvx. Okay, this is basic mechanics, Newton's law. Action reaction. Okay, so we need to find the expression for the pressure. Okay, so now we need time. Let the time interval between two successive collisions. Okay, suppose this is a wall. First it collide, okay, then it goes and come back, collide again. So what is the time for this? I call that time as delta t. Okay, we know that the collisions are perfectly elastic, therefore there is no change in momentum. The mass remains a constant, which means there is no change in speed. Therefore the time delta t will be equal to distance traveled between two successive collision divided by speed or velocity of molecule. Okay, more specifically speed. Okay, speed of the molecule. What is the distance traveled? We already mentioned this cubical box which we have considered having a length L, right? So first this molecule collide, it will move a distance, this will move a distance L backward, and it will comes to collision with this wall, and again it goes like this. So between two successive collision, it come back a distance L and again a distance forward L. So total distance will be this 2L divided by speed of the molecule, which is nothing but Vx. Okay. So this is the time between two successive collision. We know that in each collision, the gas molecule will impart some force on the wall. So force exerted by a single molecule on the wall. I can call it as some F single. Okay, so that force exerted by the single molecule will be change in momentum divided by the time taken for it. Okay, so what is the change in momentum? We have just calculated. Change in momentum of the wall is 2 mvx divided by the time taken for it, which is 2L by Vx. So if I take 2 will cancel, mvx square divided by L. This is a force exerted on the wall by the single molecule. Change in momentum of the wall divided by the time taken between two successive collision. Okay, so this is a force exerted. So we have n molecule, right? So all the molecules are moving in random, and they are moving and they collide each other, and they are colliding with the wall. So total force on the wall due to all the molecules. I could write that total force as F, capital F, which will be equal to summation Fi. This Fi belong to this. Okay, that is equal to M and L are constants because the length of the container is not changing. We are assuming all the molecules are identical and their mass is small m. So ml, but their velocities are random, so we cannot say all having same velocity. So we have to submit over the state I2, whatever be the number, we have to incorporate that number. That is equal to, that is m by L Vx square of the first particle. So I am putting Vx1 plus Vx square of the second particle, and so on. Okay, so this is equal to, I am just dividing with the total number n, and I am multiplying with the n. Any problem? No problem. So I will get mn divided by L into, what is this equal to? Sum of squares of velocity divided by total number. So I can say that mean square velocity. Okay, x component of the mean square velocity, I can say. So I could write it as Vx square, its mean, Vx square mean, which is nothing but mean square velocity. Okay, x component only. Okay, if we take the mean of the velocities, what happened? That will definitely 0 because the random motion. So if a molecule moving in positive direction, suppose its velocity is 2 meter per second. If it move in the backward direction, its velocity will be minus 2 meter per second. So if you add randomly for all the molecules, that will definitely 0. Average velocity of the molecule is definitely 0. So we are making a square. Now that negative sign will be goes off, and then we taking the mean. Okay, so that is a statistical idea to get rid of that negative sign. So we now get the force. Now we are ready with the pressure. Pressure on the wall. Pressure on the wall. That will be definitely Px will be the force exerted. We have already calculated, which is Fx by the area of the wall. What is the force? Mn divided by A. Fx is by L. Mn by L into Vx square. Mean. So this is the pressure exerted. So here you have area into length. That is nothing but volume, right? So pressure exerted on the wall, Px is Mn by Vx square bar. So V is of course volume of the gas. Sorry, volume of container. There is an assumption in kinetic theory. Volume of the container is equal to volume of the gas. Therefore, V is volume of the gas also. Okay. Now we are making a statement for any molecule. For any molecule, mean square velocity. Mean square velocity, which is V bar square, will be equal to Vx square bar. Oh, I'm sorry for that. I'm sorry. Okay. Vx square Vy square plus Vz square. Okay. So this is a V square, expression for V square. For any molecule, if you take the mean square velocity, due to random motion and symmetry, we could say that Vx square bar is equal to Vy square bar equal to Vz square bar. For any molecule, this is true. Okay. So if I go for this, there will be a bar on the top. And that will definitely equal to Vx square bar will be equal to Vy square bar will be equal to Vz square bar, that will be equal to V square bar divided by 3. Hope you get. This is just 3 Vx square. So Vx square is V bar square by 3. Okay. So we are rearranging the expression for pressure using this one. So total pressure. Total pressure. Now this is the pressure on the due to the molecules moving along the x-axis, x direction only. So total pressure, if you want to get total pressure, just rearranging this expression velocity by the total velocity. So that will be P will be equal to Mn by V. What is Vx square bar? Which is V square bar by 3. So this is the expression which is Mn by 3V. This is volume into V. I am just writing this mean square velocity. If I take the root, which is nothing but RMS velocity. Sum of squares of velocity divided by total number, mean square velocity. Once I take the root, I get RMS velocity. Square root of sum of squares of velocities divided by total number, mean square velocity. So this is nothing but V bar square, right? So V RMS square. So this is the expression for pressure. I request you to by heart this expression. From this expression, every gas laws can be derived. Okay. We need not by heart anything. Just by heart this expression, we can derive all things. So once again, the pressure expression P will be equal to Mn by 3V, which is V RMS square. So what is P? Pressure of the gas exerted by the gas on the wall. M is the mass of the molecule. N is the number of molecule. RMS is the root mean square velocity of the molecule. And a V, which is volume of the gas molecules. Okay. Now, some statements we have to say about this. So better to remember PV equal to 1 by 3. So this is an easy form, Mn into Vrms square. So this is more easy to remember. PV equal to this. Okay, that's up to you. Your choice. You can by heart any one of this expression. Okay. Now some statements about this particular pressure. Some comments I have to make. First one is our root mean square velocity Vrms square is actually proportional to temperature. How do you get this? This actually coming from Maxwell velocity distribution. For instance, you just keep in mind Vrms square is proportional to temperature. Okay, T is the temperature of gas. Temperature of gas. So what I get is P will be proportional to Vrms square for a given mass and volume. So I could write P is proportional to Mn by 3V into T. Okay. So pressure is proportional to temperature for a given volume, for a given mass. What is that actually that law tell you? For a given volume, pressure proportional to temperature, nothing but Stall's law, right? So we will come to that. Anyway, you keep in mind this Vrms is proportional to temperature of the gas. Now, next points. If V and T are constants. Okay. If V and T are constant, then we can say P proportional to just Mn. What is Mn? Small m is the mass of the single molecule, N is the number of molecule. So this quantity represents mass of the gas. Mass of the gas. So P proportional to this. Okay. Suppose I am holding constant mass and T held constant. T is constant. If you remember your high school classes, if T held constant, P proportional to 1 by V, it is nothing but Boyle's law. Okay. So by treating the two variables constant, we can find the relation between pressure and the other variable. Okay. So that's all about the concept of pressure of the ideal gas on the container. Okay. Now we would like to give the relation between pressure and kinetic energy. Pressure and kinetic energy. We got the expression for the pressure as P equal to 1 by 3 Mn by V into Vrms square. Okay. So this is nothing but the total mass of the gas. So Mn represent total mass of the gas. Mn total mass of the gas divided by volume. This is nothing but rho, density of gas. Density of gas. So we can also write this is equal to 1 by 3 rho Vrms square. Another expression. Okay. Anyway, let it be there. Now we have our kinetic energy, which is half m Vrms square. If I dividing this kinetic energy with volume, so this is kinetic energy divided by volume. So this is E, which is also 1 by 2. Okay, let me write this as for n molecules, this is Mn. Okay, otherwise we will be confused. Mn Vrms square. So this is nothing but rho Vrms square. Kinetic energy per volume. Okay, so I have E equal to 1 by 2 rho Vrms square. So if you divide these two, P by E, what is E? Keep in mind kinetic energy per volume. So this is equal to 2 by 3. That means P equal to 2 by 3 E. E is kinetic energy. I can say E. I am putting E instead of K. I am putting E. Okay. E is the kinetic energy by volume. This is the expression for pressure and which is the expression connecting pressure and kinetic energy. Okay. P equal to 2 by 3 E by V. JAM students, these are your questions in MSc entrance examinations. So try to by heart this expression. Okay, I'm not compelling you, because if you know the expression for P, everything can be easily derived. Okay, so P equal to 2 by 3 E, where E is the kinetic energy, not total energy. If you say it is total energy, no problem, because by assumption of kinetic theory of gases, the interaction between the gas molecules are neglected, which means there is no potential energy. All the energy possessed by the gas molecules are coming from their kinetic energy. Okay, so this is also equal to total energy. No problem if you say this is total energy. So that's it. This is the expression for P, which is 2 by 3 E by V, or PV equal to 2 by 3 E. Okay, and now we are in a position to discuss about various gases law, and before we will spend some time on different speeds, various, okay, this is too heavy. Okay, various types of, sorry, types of speeds possessed by of gas molecules. Okay, first one is root mean square. Root means square speed. Okay, it is defined as square root of mean of squares of speed possessed by different molecule. Okay, that is a definition. Square root of the mean of squares of the speed possessed by, I'm sorry for that, different molecules. So the definitions are very important. Sometimes theoretical questions are come. That's why I'm introducing that definition. Square root of the mean of squares of different speeds possessed by the all the molecules. Why we are taking this? If you take the average of that, then that definitely may leads to 0. If you take the velocities, now we are dealing with the speeds only. Okay, now by definition, VRMS will be equal to square root of mean of squares of velocity. Suppose first particle having velocity v1, second with velocity v2, third with velocity v3. We are taking squares of velocity of the all the molecule and then taking the mean. Okay, so we will get square root of squares of means of velocity. Okay, so from kinetic theory of gases, you have an expression for P, which is 1 by 3 rho VRMS square. So from this, VRMS can be equal to 3P by rho. 3P by rho. So now you can have some connections where rho is total mass of the molecule divided by its volume, and you can use here. So we can have several expression for VRMS. VRMS equal to first one, which is 3P by rho. If you substitute rho equal to m by v, then that is definitely 3 PV by m. But you know, by ideal gas relation, PV equal to for 1 mole of gas, which is RT. So that is equal to root of 3 RT divided by M. Okay, 3 RT divided by M. So your R is nothing but NA, Avogadro number into K. So if you rearranging your R by this, what do you get? And your M by M is M into N. If I take for 1 mole, this is M into Na. Then if you substitute R by this, then your R by M is just R by capital M is just K, Boltzmann constant by small m. So this is equal to root of 3 KT, where K is the Boltzmann constant. So I am putting a suffix KBT by small m. Okay, so KB. Boltzmann is a scientist who sacrificed his life for the physics. His theories, his ideas, when he presented in front of the science community, initially they won't accept. And this is one of the reason of his suicide, but this is not only the reason, and his physical health condition also makes some depression, and finally he suicide. So we have to respect that guy. So KB, okay. So these are the several expression for RMS velocity. Okay, one of the book, I forgot the name of that particular book, in statistical mechanics, start with this sentence. Boltzmann sacrificed his life for the statistical mechanics. Okay, so if you study statistical mechanics, okay, anyway, these are the expression. You should be very careful about these two types. Okay, this is dealing with a single molecule. Okay, here for a single molecule, then KB come into play. For a group of molecule, then the R will come into play. Okay, R by M, KB by small m. Okay, so you should be very careful, where KB is the Boltzmann constant, R is the universal gas constant. Okay, now you can see that our VRMS, which is proportional to square root of the temperature. As temperature increases, VRMS will increase. And also our VRMS is proportional to 1 by root m. M is the molecular weight. Molecular weight. Okay. And one important point you should keep in mind that VRMS is, I will write it in a different color. VRMS is independent of the pressure of the gas at a constant pressure. I'm sorry, at constant temperature. Okay, at a constant temperature, which is independent of the pressure of the gas. VRMS is independent of pressure, provided temperature should be held constant. Okay, if you fix this, then that term will be a constant, because all other things are constant. Then VRMS should be a constant. Then that will be independent of whatever be the pressure exerted by the gas molecules on the container. Okay, so that point you should keep in mind. Okay, and experimentally it is proved. And next, speed, most probable speed. Okay, we will define it because it is very important. It is defined as the speed which is possessed by maximum fraction of molecules present in the container. If you have 10 molecules, say, sorry, 100 molecule, and 70 molecule possessing 10 meter per second velocity or speed, then that is the most probable speed. It is a speed possessed by maximum fraction of molecule. Okay, so most probable speed is defined as the speed possessed by maximum fraction of total number of molecules, total number of molecules of the gas. Okay, maximum fraction of number of molecules of the given gas. And this is actually derived from Maxwellian distribution. So most probable speed, I am giving you the expression right now, straightforward, which is 2p by rho. You keep in mind. The last one is 3p by rho. Now it is just 2p by rho. Now from here you can build, your rho is m by v. So this is definitely equal to 2pb by m. For 1 mole of a gas, what is PV, which is equal to RT? So 2 RT by M. If you change in terms of Boltzmann constant, that will be 2 kBT by M. I hope this discussion is very clear to you because we have already discussed this fact here. Okay, I'm just taking the analogy and moving forward. Okay, so this expression you should keep in mind. This is the expression for most probable speed. Now we have one more speed, which is average speed. Average speed. This is not average velocity, average speed. What is the average speed? Arithmetic mean of the different speed possessed by the molecule. So this is the arithmetic mean of the speeds of molecules in a gas at a given temperature. At a given temperature. So what is V average? Arithmetic mean of different speed, V1 plus, V2 plus, etc. divided by N. Suppose N molecules are there. If capital N molecules, then you have to use capital N. Okay, I am better to use capital N because we have already taken N molecules, right? So capital N, that's it. So average speed, which is 8p by pi m. Pi rho, I'm sorry, pi rho. 8p by pi rho. This is equal to root of 8 PV by pi m. So hopefully you can write it 8 RT by pi m or 8 kBT by pi m. All the expressions are, I'm sorry. This should be small, right? Yes, that's small. So single molecule. So this is the expression for average velocity. So comparing with these three velocity, you can compare with the last term, right? What is Vrms? Vrms equal to root of 3 RT by m, and V most probable root of 2 RT by capital M, and V average equal to root of 8 RT by pi m. Pi is around 3.14. 8 by pi is around 2. Anyway, it is greater than 2. So if you compare all this velocity for a given temperature, for a given mass, then you will get Vrms will be greater than V mean will be greater than V most probable. In a CSIR examination, they asked this. Not even in IIT JAM, in a CSIR examination. If you have a molecule, gas molecule confined in a well, what is the relation for Vrms, V mean, and V most probable? This is a relation. RMS speed is greater. Okay. So this is all about different velocities possessed by the molecule, and we will come back to this point once we discuss Maxwellian distribution. Okay. we will discuss it in kinetic theory and as well as in statistical mechanics. So here we go for different gas laws. Derivation of different gas laws from kinetic theory of gases. Okay. First, I would like to discuss about Boyle's law. Okay, now we will introduce in a slightly different way. What is Boyle's law say that? Telling to you, at a given temperature, the pressure of a given mass of gas is inversely proportional to volume. For a given T, temperature, pressure is inversely proportional to volume. I am not telling the statements. Okay. For a given T, P inversely proportional to volume. So I could write P is 1 by T for given T. And I can write PV equal to a constant. PV equal to a constant. So this is the definition which we already know from the high school classes. And now I would like to derive it using the kinetic theory. Okay. So here we go. We have, by kinetic theory of gases, PV equal to 1 by 3 Mn Vrms square. But we know that Vrms square is proportional to temperature. So for a given Vrms or a given temperature, we could write PV equal to 1 by 3 Mn T. No problem. We can introduce T. So for a given T, if you look into a given mass, you can see that for a given mass is a constant. For a given T, temperature is fixed. So PV equal to a constant, which means P proportional to 1 by V. That's it. So this is the result. PV equal to a constant, or P proportional to 1 by V. Okay. So we can discuss more about it. I could write my PV as pressure into my density is mass by volume. So volume will be mass by density. So this is nothing but M by density. So this is equal to constant. Okay. So M is already a constant mass. Therefore, P by rho equal to constant. So equation of state, if you write equation of state, you can write PV equal to constant as well as P by rho is equal to constant, which means if you put a gas in a container at a given temperature, its pressure may change and volume may change, provided this remains as P1 V1 equal to P2 V2, or you can say P1 by rho 1 equal to P2 by rho 2. So this is the equation of state. Okay, now we are interested with the graph. What would be the graph P versus V? P versus V graph. P is inversely related to V, right? Therefore, that graph will be P against V. This is drawn at a given temperature, so that will goes like this. Okay, what happened if temperature changes? We will come to that point at the end of kinetic theory of gases. We will analyze this graph very carefully. For different temperature, what shift will occur, we will discuss. For now, this is just a rectangular hyperbola, P inversely related to V. Okay, so if I draw a graph PV against V or T, P or V. PV equal to a constant, whether it is P or V, no problem. This is fixed. So these are the two graphs from Boyle's law. Now we are moving with another law called Charles law. Charles law. So this is, the statement goes like this: for a given pressure, we are fixing the pressure constant, a given value. The volume of the given gas is proportional to its temperature. For a given pressure, volume proportional to temperature. This is Charles law in a nutshell. So we know that PV equal to 1 by 3 rho. I'm sorry. Okay. Mn, which is mass into Vrms square. Okay. This is the expression for pressure of the gas. Now we are fixing the pressure as a constant. Then we need volume and temperature. So we know that our Vrms square is proportional to temperature. So if you fix our pressure as a constant, these guys are also constant. So you get your volume is proportional to Vrms square, which is proportional to temperature, which means for a given P, if you fixed your pressure, volume will be proportional to temperature. So what is the equation of state? Okay, I will come back to equation of state in a moment. And before that, I will go to the expression containing density. Okay, now P equal to 1 by 3 rho Vrms square. Okay, so Vrms is proportional to temperature. So P or 3P equal to, or 3P equal to rho into T. We can write this. Vrms is proportional to temperature. So we can approximately write this equation. For a given pressure, if you look, this is constant. So rho T equal to constant. So equation of state, we have two equations we can write. One is rho T equal to a constant. And another one is which is V by T. Volume proportional to temperature, which means V by T equal to a constant. Okay, these are the equation of states. If you plot a graph, volume versus temperature. So V equal to a constant into T, right? Therefore, that will be a straight line. As you increase the temperature, volume will increase. And you can extrapolate to the center. And if you have Vt or V by T, if you plot against the temperature or volume, no problem, because V by T is fixed, is a constant. So that will be a straight line. Okay. Now, third law, which is Gay-Lussac law. Or pressure law. Okay. So what is the law says? For a given volume, we are fixing V. V is constant. The pressure of the gas is proportional to temperature. This is the idea of this law. From kinetic theory, we know that PV equal to 1 by 3 m V Rms square. Okay. So we are fixing our volume. So Vrms is proportional to temperature. So you can see m by 3 is again a constant. Therefore, P proportional to T will come from the kinetic theory of gases. So from this one, we could write P by T equal to a constant. So our equation of state we are fixing volume constant, then we get P by T equal to constant. The P by T will be a constant. So if you plot it, your pressure, your temperature, so P equal to a constant into T, therefore this will be again a straight line. Okay, now we can extrapolate it to this origin. That depends on what is your constant. Depending on that will change. And if you plot P by T against P or T, no problem, because P by T is a constant, that will be definitely a straight line. So that is all about our equation of state. Okay, so I think you are very familiar with these laws. For JAM students, these questions are coming directly. You can easily answer. Okay. Now our new concept, Avogadro Law. Avogadro's law. So the law says at the same temperature and pressure, equal volume of all gases containing same number of molecules. So that statement is important. At same temperature and pressure, equal volume of all gases contains equal number of molecules or atoms. Okay, so this is all about Avogadro's law. Suppose we are taking say two different gases. Okay, say let M1 and M2 are molecular weights. Okay, and I'm taking N1 and N2 number of molecules. Two different gases with a different mass, different number of molecules, and we are keeping same temperature and pressure, P and V same. Okay. Now Avogadro law says that they will containing equal number of molecules. But from kinetic theory, we know that our PV equal to 1 by 3 Nm Vrms square. So for the first gas, we get P1 V1 equal to 1 by 3 N1 M1 Vrms square. So for the second one, why Vrms square is, okay, wait. P2 V2 equal to 1 by 3 N2 M2 Vrms square. I am putting Vrms square is same because we are considering, okay, I am not saying that this temperature is same, right? So I am changing. I'm sorry for that. We are just fixing pressure and volume as a same, right? Okay, we are fixing the gas molecules in a given volume container and such that their pressures are same. Now I would like to write this is V1 and V2. Okay, if temperature is same, then Vrms should be same. Okay. Can we say that they are same? No. Even though temperature is same, we cannot say. Why? Vrms inversely related to root m. So we cannot say. So it not only depends on temperature, it depends on molecular mass. So V1 and V2 will come. Okay, anyway, let it be like that. Where V1 and V2 are RMS speed of the molecules of the gases 1 and 2. Okay. Now we are fixing same temperature. Fix same temperature for each gas. Okay. Then if you fix the same temperature, what happened? Average kinetic energy of the molecule will become same. That is, kinetic energy average for the first molecule will be same as kinetic energy average for the second molecule. Okay. So which means half M1 V1 VRMS actually square will be equal to M2 V2 square. From here you get M1 V1 square equal to M2 VT square. They are same. Now if you divide these two expression, you are fixing the pressure and volumes same, right? So P1 V1 will be equal to P2 V2 because pressure and volumes are same. And your half mv square, so that is M1 V1 square is equal to M2 V2 square. They are also gone. 1 by 3 will cancel each other. And that will gives you N1 equal to N2. What is N1 and N2? Number of molecules. So that is nothing but Avogadro's law. At the same temperature and pressure, equal volume of all gases. If you fix the volume, and they will contain equal number of particles. Okay. Suppose this is 1 mole, then that will contain Avogadro number of particles. Okay, I will tell that concept. This is very simple concept, basic one. Anyway, I will just come to that point. 1 mole of a gas contains Na, which is Avogadro number of units of atoms. The gas may not be atom, sometimes it may be molecule, then molecule. 1 mole containing Avogadro number of units. Avogadro number units of atoms or molecule. Okay, what is Avogadro number? You are familiar with that number also. 6.023 into 10 power 23 mole inverse per mole. In 1 mole, you have this much particles. Okay. So how do you calculate the number of moles? It is very important in our calculation. Let it be n number of moles. Then what do you have to do? Number of molecules or atoms divided by Avogadro number. Okay, that is n by Na. Total number of molecules will be equal to number of moles into Avogadro number, because 1 mole containing Avogadro number, then N and Na will be same. Suppose it containing 2 mole, then 2 times Na will give you total number of molecules. Okay. So to get a different expression for this Avogadro number, I'm sorry, the number of moles, I'm introducing the concept of molar and molecular mass. Okay. So molar mass. What is molar mass? Let it be M. Okay. It is a mass of 1 mole of substance. Mass of 1 mole of substance. Okay. Then N can be written as mass of the given molecule in gram or given atom in gram divided by molar mass. Divided by molar mass. How do you get that? N equal to, you know that N equal to N by Na, right? If you multiply with M and dividing with M, what is the numerator equal to? This is equal to mass of the given substance. Given substance containing n number of molecules, therefore Nm means mass of the given substance. In the denominator, you have Na into M, which is nothing but the molar mass. Okay, so we can say that Mass of the gas divided by molar mass of gas will give you this N. So you have different expression to calculating the number of moles. If you're having number of particles, then just divide N with Na. Or if you're having the molecular mass of the substance or molar mass are given, then just divide mass in gram by molar mass. Okay. So your total mass will be mass of a single substance into Na. Okay, this is mass of individual molecule. This is mass of Avogadro number of molecule, 1 mole of substance. This is molar mass. Okay, that's it. This is all about our Avogadro law, and we will come back to the discussion of moles later. Okay, I think we can wind up our discussion with the 2 more concepts. Okay, wait, it's very important. One is Graham's law of diffusion. Graham's law of diffusion. The law says like this: when you have 2 gases at the same pressure and temperature, given temperature and pressure, you are allowing those gas molecules to diffuse together. You are trying to mixing it. Then the rate of diffusion will be inversely proportional to the density. That is given by the Graham's law. For a given temperature and pressure, if we mix the gas molecules, then rate of diffusion, which is proportional to square root of 1 by density, 1 by square root of the density. I'm sorry, this is square root of density, not 1 by density. Yes, square root of 1 by density. Okay, correct. So R, the rate of diffusion R, I'm sorry, R proportional to 1 by root rho. And the law having a different statement, a different form, the rate of diffusion is also proportional to this RMS speed, Vrms. Okay, that is also true. What is Vrms? Vrms is equal to root of 3p by rho. So from that you can get the relation R proportional to Vrms, but it is proportional to 1 by root rho. So everything will be matched. So keep in mind R1 proportional to 1 by root rho, inversely related to density. Okay, not R1, just R. R is enough. And R is also proportional to Vrms. So this is Graham's law of diffusion. Okay, in a previous MSc examination, they asked this one. Okay, that's it.